I am Dr.C.Nirmala, Associate Professor of Physics, Holy Cross College, Autonomous, Nagarkoil.
Nuclear forces, understanding the fundamental interactions in atomic nuclei. The nucleus is held together by the strongest force in nature, the nuclear force. This fundamental interaction binds protons and neutrons, overcoming electromagnetic repulsions to create stable atomic nuclei. Understanding nuclear forces is essential to comprehending the structure of matter itself. Nucleons and their interactions. Protons and neutrons, collectively called nucleons, are the constituents of atomic nuclei. Here, the strong nuclear force, a short range but powerful attractive interaction exists. This force acts between all nucleons regardless of their charge and approximately 100 times stronger than electromagnetic forces at nuclear distances. Charge independent proton-proton, neutron-neutron and proton-neutron forces are nearly equal. Saturation character, each nucleon interacts only with its nearest neighbors. Contains both attractive and repulsive components. Tensor forces and the key characteristics. Range properties. Nuclear forces operate over distance of 1 to 3 Fermi. Beyond this range, they decreases exponentially. The force strength. At nuclear distances, the strong force is approximately 100 times stronger than electromagnetic force. Saturation property. Each nucleon interacts primarily with its immediate neighbors rather than all nucleons in the nucleus. The deuteron ground state. Binding energy analysis. The deuteron has a binding energy of 2.224 million electron volt, relatively weak compared to other nuclei. This low binding energy indicates that the deuteron is just barely bound. Ground state has total spin of triplet state J equal to 1, positive parity and even angular momentum. Electric quadrupole moment indicates non-spherical charge distribution. No bound excited state exists. Exchange forces. Heisenberg proposed that nuclear forces arise from the exchange of particles between nucleons and analogous to how proton exchange mediates electromagnetic forces. Exchange mechanism, Pauli exclusion principle and saturation potentials are some important discussions. Meson theory of nuclear forces. Yukawa in 1935 proposed the meson theory and the exchange particle called mesons with mass is 140 million electron volt per c square. The range is in the order of 1.4 Fermi. Particles are exchanged during the nuclear force. Yukawa potential V of R is given by minus g square e power minus mu r divided by r, where g is the coupling constant, mu is the inverse range parameter. Nucleon scattering. Here the accelerators produce beam of protons or neutrons with controlled energies are projected, and low energy neutron proton collisions occurs below at 10 million electron volt energy. Phase shift analysis. The changes in wave function phase caused by the nuclear potentials. Effective range theory. The scattering parameters developed by Springer and Bethe parameterize low energy nucleon scattering using two key quantities, scattering length and effective range. Charge independence and isospin formalism. Charge independence in nuclear force is approximately proton-proton, neutron-neutron and proton-neutron forces. The symmetry suggests that proton and neutrons are fundamentally similar particles. Isospin formalism explains a quantum number analogous to spin but operating at the abstracted charge space.